only the content changes, I suppose. Yeah.
Well, you get to teach some things at a lot higher level.
Yeah, it's always with respect to the students, right? Yeah, I mean, there's no high level. Like I taught in a high school for 2 years.
I saw that. I was looking at your bio.
Yeah.
And,
So that was I would say, rewarding experience, or I had a different perception of the altogether, and maybe it was the students I had a nice.
I think that kind of broad perspective just brings a lot to the experience, how anyone does what they're doing.
Exactly. Yeah.
I did remedial classes when I first started.
You did what?
Remedial classes.
Remedial means
like remedial math and stuff like that. And it teaches you about patience than you typically have coming out of graduate school.
I can imagine.
Well, I think that teaching at a high school is going to be a similar experience, because you still you have to go, you have to put take a lot more burden on yourself.
Exactly.
And then as you go higher in the levels, it's like if there's a thing you're lacking on, then you need to figure out what it is.
No, that's the right way to put it. Yeah, you have to take it out on yourself. Here it is. That's up to you, kind of.
I think your voice has changed.
Tell that again?
I think your voice has changed.
Oh, voice has changed.
No, I think you have a cold or something.
No, not that. Maybe it is right from the shower or something. Sometimes, like everyone tells me when I wake up and I'm on phone, you sound different. And maybe I took a quick shower and I didn't clear up myself.
The thing is, if you just wake up and speak, you kind of sound like a drunk person.
Yeah.
But this is different.
Oh, this is
Like,
different.
this is like you had cold or something.
Oh, okay, not that I'm aware of, but okay, that's not good. Hey guys. Yeah, that's not good. Leah, Michael, and Jordan is probably there. I think. Yeah. Okay. Oh, I should show you the classroom so that you guys at least know.
Can I submit the homework later today? Like a few hours after this? I missed due to a deadline.
Oh, due to a deadline. Do you have it now?
I don't have it. I have written down, but I have one quick question to ask you.
Yes, you can. Here is a challenge that comes up. On D12, I had to do a lot of work to postpone. Here, I just accept it. Right? Oh, late. Okay. So I just accept it. But I think on D12, I had to go and change the dates, this and that. So I have been telling everyone that no due dates, because it gets too hard to organize those things. So yes, once, but it may not be like usual semesters. So like usually I'm pretty lenient, I understand. What you should do is you should talk to each other. Talk to each other. Everyone says I'm fine. That's easier than going and changing deadline for one person. So if that's understandable, that's clear.
Well,
so just talk to each other. You guys have a group or something?
As far as I can say, Moses would be happy.
Okay. Yeah, so that's what you should do, yeah. So the suggestion was that they wanted, or Avinash wants an extension on the homework by until evening or something. So, so I was saying, if the whole class is fine, I'm okay with that.
Yeah, it's fine.
Yeah. And send me an email saying that you guys want to postpone it, because D2L submission, unless I change it, you won't be able to submit it. It's a little more organization. I have to find the time. So even though it's a half-a-minute job, you have to orient yourself for that. Yeah. Okay.
So I know ways that you can do the submissions on D2L is you you have a deadline, but it stays open for submission. So you can continue to submit.
Actually, yeah, that's a good point. Yeah, and as far as I can see, you can still submit on D2L.
Okay. Because I know whenever I emailed you about the one thinking it was due at the end of the day and not the beginning, I couldn't actually submit it. Otherwise, I would have submitted it. It said closed. So maybe it was different on those than this one.
So check it out again, because I have got submissions that are 2 days late.
Okay.
So it should be possible. So check it out again so that then I don't have any problem. Then I decide later on whenever I'm working on this, that what should I do about this delayed submission.
Okay.
Then it's not pressing. Every time someone submits, I have to go to the computer and do it. That's my only issue with that. Is that reasonable?
Mm-hmm.
Yeah. So try to submit it. Okay, yeah. Avinash, you try to submit it and let me know how it goes.
No, I'm done. I'm done with everything, but I just had one question.
Yeah, but you will have to submit it. At that time, it will be closed most probably. And let me know how it goes, the submission. Yeah. I received late submission, so obviously it is possible.
So I'm looking at it right now and it says homework 2 closed September 4th at 11 a.m.
But try to submit it anyway.
You can't even click on it on the link anymore.
The whole other submitting, I think, what is it? If you don't, I mean, one of you guys submitted late, right? I don't want to take the name.
Maybe they submitted in a different Dropbox.
What is a different Dropbox?
Like submit.
Do you see my screen?
Yeah.
See how homework 2 can actually access the link anymore. It says close September 4th. So if you wanted to submit it, you wouldn't be able to. Maybe it's just different on some of your other classes or whatever. I'm not exactly sure.
No, I think it was either this or A.
Here's a good, for instance, homework 1 still is open, see? So whenever you made the file, you must have made it.
So homework 1 is still open. Okay, so there is some change I made.
I could click on homework 1, you know, and then I could still add a file. It looks like this one, but some of these other ones, no, I can't. So
there's some difference between the two. Okay, I'll have to look and see. There's one more due date saying that end date. That's something that I might have changed. So maybe that's what the difference is. So I'll look into it. Yeah. So yeah, hopefully before but don't. If it is not available by 4 o'clock, don't give up. Go until 12 o'clock in the evening. So Moses, you came late, so there was a request for delayed submission.
I was going to request the same thing.
See, I told you, Moses is going to be.
Listen to the recordings of my opinion on that. I don't have an issue. I've been lenient. You guys know that. It's just that on the computer, it's a little. I mean, again, it seems like whining, but it is a big hurdle if you've gone through it. But suddenly, if something is due on 12 o'clock, then it becomes a lot important, even though it is 1 minute, and you have to give up everything and go for it. So I kind of put that. But probably, I think I know what now that Jordan showed me his file. I think I can make that end date extended. Then I also know how much late it was submitted, so that's recorded also. Then at some other point, I can decide what I should do about it. Okay, that's, I think, reasonable. Okay. Any other comments? Oh, you're not on the. 3 students. Yep.
Actually, when you said something about, getting groups together, we actually started that discussion on getting, on Monday, we were discussing having informal meetings to discuss any problems we were having.
That's nice. And so I think there was a discussion about that sometime back. I'll leave that to you guys. I think you guys are dealing. From what I noticed, it is better that I don't involve in it. That you guys do everything on your own. But yeah, I will encourage it. Remember that this is you can look into each other's work and it's not, it's considered, I think it's healthy. Now someone else might say that it's not healthy, but at least in my course, I would like you guys to look into each other's, but at least write your own work and be responsible enough that yes, I looked into someone else's work, so I had to work on it extra. That's the way I say it. And this is the same thing I say for introductory level physics courses in my introductory level physics also. Especially this semester, it is like that because it's open book, open resource, everything. So the only thing I don't allow is during the exam, you cannot take help from someone. I don't know how to word this yet because the exam is next week. Someone that can speak or someone that is intelligent or someone whom you speak, it is unfair to your peer, or something like that. I find a word for it. Yeah. So that's the basis I'm making. So that then cheating becomes, it's not possible, kind of, less possible. Okay, yeah, but all this is perception. Okay. So, yeah, thanks for that homework information. So I'll try to make the homeworks due on the date I tell, and you should be able to submit it later on. That doesn't mean that I'll penalize it, but I'll decide sometime during the semester that okay, how much of misuse has been happening of that. So usually in this course, I've seen you only learn more if you spend more time on it. So it's reasonable, but at the same time, you have to be fair also to everyone. It's a small balance, but usually I depend on giving the time, extra time. So homework 2 was, homework 2, let me write that again. Possible to submit, right? Submit. I'll probably make it about 3 weeks forward. But again, having said this, even though I don't mind delay, I would also say that you should submit it in time because this catches up. And again, that is your responsibility. But at the same time, if I push you guys on it, it helps a little. So if I put a deadline, then you guys submit it. There is a lot of people who follow. There is more time, then I'll take more time. So stick to this, let me put it like this. I'll make an opinion in my own self that, okay, how responsible you guys are. So if you guys are always submitting usually in time, that's good. Then I know that, okay, you've been regularly doing this. So let's put it that way. So possible to submit delayed. I don't know if that's the correct sentence or not. Okay. But I haven't set it yet, as Jordan pointed out. So I will do that. Should be possible to do that.
I think there was also a lot of confusion in the last class about, how to handle those.
See, that is, yeah, I wanted to stress on that, and I want to point that out, that we are not using that feature here in the problems that we are doing. Or maybe I should also point out, by homework, what do you guys think? There are 4 things on that list, right? There was a confusion among one of you guys yesterday, I noticed. That is homework 2. I'll come back to what you said, Jordan. There's a homework 2, then there are some resource materials. Resource material 1, 2, 3, or delta one, right? These are not due. I hope there was no confusion, but one of you guys did have a confusion, and I noticed that they worked on it for a long time. These are not due. That's just for help. So homework 2 is relatively shorter, and even though I created some confusion in the class last time, that is on a more advanced level. We will see that in the next semester or so, but you shouldn't be needing all those theorems, if you want to call me theorems, in this homework. Okay. But nevertheless, since you pointed out, let me address that a little bit. Okay. So let me address at least a question like that, and then maybe proceed forward. Reasonable? Yeah. Okay. So that is a homework preview. It is on September 11. Oh no, it's only 10 minutes, right? I thought it was 40 minutes. So on Monday, following Monday, we have the exam.
Excuse me, Professor.
Yes, please.
I have a question about the exam. During the exam, if we need extra time, can we have it?
Oh, that's correct. That depends on everyone else, whether they are available or not. Before that, we had actually even decide whether it's going to be in the class or not. Let us say that, so I noticed that the cases are increasing in the campus, like it has gone to 30. That raises the question, is everyone comfortable coming to the classroom and taking the exam? What I can do is that I can split it into two or put you guys in two different rooms. So there is minimal interaction. You come here and then go, but still that's a whole, you come into a city for some of you guys. So give me suggestions on that. How do you get, or if you guys are comfortable talking about it, we can talk about it for a few minutes. Like, is there any suggestion on that? Are you guys comfortable coming and taking it in the class? That's my question.
For me, personally, I'm in a little bit different place maybe than most of the people, just because I'm more of a high risk case with my wife. And if I get it somehow, then I bring it to my wife, then her whole school gets it, basically, if I don't know about it. But I mean, I would still come to campus if that's what I needed to do or whatever. But
so here is how we can do. Okay. Again, I'll make it optional. Let me put the responsibility on you guys. It's up to you guys whether you want to come to the class or not. But if you're not coming to the class and taking it, it is your responsibility to give me a clean way of taking the exam. That means you have to put a camera or do whatever you want. It should be very unambiguous from an instructor's point of view. You guys all are instructors on your own level at some stage. That I shouldn't have any confusion. I don't see anything in this class. I know most of you guys, so I don't see such a problem. But still, there shouldn't be any source of doubt. You set your camera, you do everything, you be responsible about that, and give me a way of, so that a third person looking at it or another, your peers looking at it, shouldn't feel that I've been unfair. Right? Is that reasonable?
yeah, for me, for sure.
And that should be possible with this simple system that we have, right? Since we are only 6 of us, right? Khaled, anyway, you have to do that. And you have to tell me beforehand how you do it. And it will be my own consciousness that I'll decide that, okay, this is not acceptable, so I won't accept the exam, and then we will work on it something else later.
So, and also, I have another thing to say with the, sometimes when you give take-home exams as well, I feel like sometimes they can be better because sorry, my dog's going crazy. Sometimes you can make them a little bit more difficult. And I guess the process of thinking about the problems is more beneficial, and I feel like I learn more. But I guess if it's specifically just from like, to see where you're at type deal, if that's what you're looking for, then, you know.
Yeah. I am also for take home usually, but I should come up with questions also which are easy to assess take home. It is usually harder to assess or prepare questions that are take home style. That's my challenge. Okay? Like most of the questions that I've given before are already online, so that doesn't serve the purpose very well. But I do make it, and I still have about 10 days left, so maybe I will do that. But if it is the classroom, that's my question. Okay? So that is a good chance that, yeah, I'll make it take home, but let's assume that it's not take home. Same thing holds for 500A also, the other course also. Until I make the question, it's not ready there.
And I was thinking too, because one of my fears was like next week, they're not releasing the new numbers until late on Wednesdays. And if we made a decision late to do a take home or to come to the campus, say we made a decision to come to campus for math methods, but say the numbers increase at the same rate and there's now 100 students on campus that have it, the risk factor of,
No. That should never, exam should never be a reason for you to take a risk. That I will surely say. But I'm saying the only thing I'm requiring is that if you're at home, make a method to take the exam. Don't make it take home, but instead use a camera system to take the exam with invigilation. Keep that room open. That's all I'm saying, right? Don't come to the campus even if you're slightly, even if it is a 1% risk you think you're taking. But that's your call. Like everyone has different ways of looking at it. So I will discourage you completely. That was the whole point, that this streaming way is so that I don't take the responsibility, is the student's responsibility. I have taken the responsibility that I'll come to the class. That's my call.
because I think with the cases on campus alone, with students at SIU, I think it's almost as much as my entire county has in cases. So,
Sure.
yeah. So I know Jackson County has a lot more than the county.
Yeah. So I will not ask you. I should not ask you. So that's very, very reasonable. So I hear you completely. But either we postpone the exam or we have to do something like that. We have to go through this course anyway, right? That's my point. So help me do this assessment. Yes.
I was going to say that just with the webcams they have set up, all they have to do is tilt the perspective so you see them working.
Exactly.
And you can see what they're doing. And
yeah, that is all I'm asking. And since it's a small class, I put the responsibility on you guys to do the invigilation with respect to others. Right? In another classroom, I do the invigilation. I say that I'll make sure. So I'm doing the policing. Here I'm saying that you do the policing for yourself with respect to others. You have to make sure that you're convincing everyone else that I'm not doing anything unfair. That's all. And again, this is a very nice set of people. I don't see anything of that kind coming up, but I'm just making an official statement here. That's all. Does that seem reasonable? Right?
Excuse me, doctor. Is the camera system you are using now, is it, compatible with the exam? Is it good for the exam, or we have to use something else?
Tell that again.
Is the camera system we are using now, you said about taking the exam while we're using the camera on us and everything. Is it good for the exam, or we have to use something else?
See, that's what I'm saying. Instead of asking me, ask yourself, right? So instead of putting this question to me, ask yourself, if someone else is looking at this camera, is there any source of doubt, right? Usually no. I would say that if there is a camera, both hands are visible all the time, your eyes are always visible. Let us say you don't even have a computer. It's very clear that you don't have any internet source around you. It's usually good. I'm satisfied with that, but again, it's not me. You're satisfying your peers. Remember that. So that's it's a source of fairness. That's my problem. Okay?
Yeah.
And all of you guys are teaching assistants, so you guys know what's going on here. So that's my problem. Okay?
Yeah. That's
yeah. Okay. Let me proceed. Okay. Yeah, so there was a question about delta function, how we use it. So before I proceed ahead, let me do at least one example maybe on that. Or here is what I suggest. I think since a couple of you submitted, right? Let me proceed and do the course. Let's begin the course because as of now, it's all mathematics we're doing. We'll be doing delta function every other day. So you will learn it. If by any chance you missed anything in whatever I said last class, it won't hurt you. Right? Okay, you'll get very comfortable with delta functions because almost every other day I use delta functions in this in the course that I teach. So let's proceed in that sense. So I think I should start the Maxwell's equation. So let's write down what the Maxwell's equations are. Maxwell equations. This was written down by Maxwell in somewhere around between 1860 and 1865. And you have seen it in some form, in integral form before in undergraduate or introductory physics course. We will use the differential form. This is the divergence of the electric field. Let me, usually epsilon is written on the right side. I'll write it in front of the electric field. Electric field is a function of position and time. And that's equal to charge density. So rho here is charge density. That's charge per unit volume. The charge. Oh, did I address that question of what is it called? Whether extra time is allowed or not? No, because that was the question that was brought up by earlier, right? I never addressed it. So the question I wanted to ask you guys is: are you guys free after this Monday and Friday? But on Monday, right after the exam, are you guys available?
Mm-hmm.
3 until 1.
Michael? I cannot hear you. Can you guys raise your hands? There is some feature on Zoom, right?
Yeah, I'm free.
Yeah, you're free. Jordan?
Yes, I'm free.
Luke?
Yeah, I'm free after Monday and Friday, but not after math methods.
Okay, but in this class you are, right? Okay.
Yes.
Okay, but not after math methods. That's a good point. And Khalid?
Yeah, I'm good.
Okay. Avinash, Moses, Rob? Okay, so that means the exam will be for 75 minutes. It will be prepared for 75 minutes. If it is an in-class exam, it will be for 75 minutes, but then you can take about, let's say, half an hour to 45 minutes extra.
So by now, you all should be ready to start.
Let's restrict it to half an hour to 45 minutes, just for all this invigilation and other things that might happen. Again, I have not decided whether it's going to be take home or not. If it is in class, that's all. Be prepared for an in-class kind of version, so because I feel I may not be able to come up with such nice questions for take home at this stage of the course. So that's my expectation in this course. Okay. But who knows? Yeah. Okay. So yeah, you can have extra time. Okay. So this is the electric field. E is the electric field. By field, we mean that it's a vector at every point in space and in time. It keeps changing. That's the idea. And the divergence of this quantity is the charge density. That's Gauss's law. And Gauss's law plays an important role in whatever, especially in introductory physics, we have emphasized that a lot. It's same thing holds here also. And at least the integral form that we use in the introductory physics course, I expect you guys to know everything in that. So that's one question that you can expect to have if it's an in-class exam. If it's not an in-class exam, again, it becomes harder because those are all available. But Gauss's law, make sure you do all the self-study of Gauss's law. Basically, the point is simple. Maybe I can ask the extra credit, right? This be familiar with this. let's say you have, let me put 3 or 2, right? So let's say this is a sphere of radius r, which is charged, right? So that's charge q spread out as a solid sphere, right? This is a solid sphere. It goes deep inside. It's like Earth, our Earth, right? It's our mass in here. And another possibility is that this is all on the surface. The same charge q, but it's all on the surface. And same thing you can ask about Earth also, right? Do we know, how sure are we that all the mass that is there on the Earth is not on the surface? It's not a shell. Earth is not a shell and it's actually a solid. How sure are we about this? Or if you have to verify this, if you have to go and verify this, how would you verify it?
The magnetic field.
Magnetic field. Why do you say magnetic field? I can generate, if there was, in fact, this is another way of generating the Earth's magnetic field. If there was a positive charge sphere, right, and if I were to make this rotate with a frequency omega, this will act like a magnet.
Mm-hmm.
Like, in fact, it only has to be on the surface. So having a magnetic field doesn't mean that there is really some magnet down there, or there is a iron core in there. But that is correct understanding. I'm not trying to deny that. But how do we know for sure that Earth is not hollow? Like if there was someone who kind of came and told you that Earth is not hollow, especially the good point is, can we measure the, if you're on Earth, right? So let's make it Earth now. So this is mass, so this is shell, right? So there's a shell now. And all the mass is concentrated around here. And let us say you're allowed to measure G. Right? G is exactly like here, the electric field, version of electric field in gravity is the G, right? The question is, can you measure G outside everywhere and decipher whether Earth has a structure or not? What structure does the Earth have? Is it possible or not? Just by measuring G, you're allowed to measure G as precisely as you want. Okay?
But only outside.
Let us say inside also. Inside you cannot go further deep, right? Yeah, good point. If you can dig it as well, you'll know it, right? Then the question is not so. Yeah, if you dig it, let's say you're allowed to dig 1 kilometer, but then I would say that, oh, there is a hollow in here which is 10 kilometers down there. Right? So the hollow is after 10 kilometers. You cannot dig 10 kilometers, right? So you cannot use that method. Yeah. If you can, yes, I think yeah, you're correct. But let's say outside, you're allowed to measure G outside everywhere, only then it serves the purpose. Can you figure out? Even a yes or no is good. Do you guys know the answer now?
I don't think you can't.
You cannot, yeah.
Yeah, you can only measure G outside. You can't determine
Yes.
whether it's hollow or a shell.
That's correct. I mean, if you have a spherically symmetric system, even otherwise, I mean, roughly, if you change, that doesn't change so much. You cannot say about the structure so much by measuring the electric field. That's why you have certain kind of systems. That's why you have to really go inside. You have to break apart something. Otherwise, just by measuring electric field, you'll be able to learn a lot about proton structure, for example. But it's not. So in that context, so that's a gravitational analog of that. But my extra credit was similarly here. So what is the electric field? So this is a shell. And this also has an electric field. And outside it will look exactly the same. That's what we pointed out. Outside it will look exactly the same. And let's say the magnitude of the electric field you plot with respect to R for this and this. Okay, what will be the difference?
The difference is that if let's say they had the exact same amount of charge,
Yes, the exact same amount of charge.
then if Q is the same, then if you imagine the left side being split up into squares, the area in which the squares are split up is basically it's gonna be less on the left than it is on the right, correct? The field will be stronger.
Here, so the field, these are two field lines, right?
Mm-hmm.
So use your Gauss's law. You can use Gauss's law and get this almost immediately, right? What's the difference in here, these two plots? I can give you a hint.
Surface is different.
Outside, it's the same. It will go as 1 over r squared. Both will be exactly the same outside, but inside, things change. What changes?
Inside is 0 on the right.
Very good. Right, so it is inside is 0 in here. And what about for the solid sphere?
I think it's linear.
Linear, that's correct. Very good. Yeah. It's an extra credit here to do that using Gauss's law. Just do a simple exercise. You should get these plots using Gauss's law. That's just a review. So that's Gauss's law for you. That is a magnetic field also. And we can talk about divergence of the magnetic field. There is no epsilon naught or mu naught is the corresponding thing, but that's not there. Usually the connection is, so B is magnetic field. Magnetic. Usually the notation is D, which is called the displacement field, is epsilon naught times electric field. And B is mu naught times H. If you're in vacuum, these are constants. Right? That is the universal constant. In fact, you can even set them to 1. So these are pretty much identical. As far as concept goes, same direction. Everything is in the same direction. There is no point in defining anything. But if you're in a material, this will become the material property. And in fact, this can even be a tensor. So in general, this is D is equal to epsilon dotted with E. Right? That means to say that the electric field in the X direction can create a displacement in the Y direction. Right? It's like saying F is equal to MA. Right? You have F is equal to MA, right? Is mass a scalar then? Could it be a tensor? In principle, it could be, but mass is scalar, by the way. But you're saying that can an acceleration in the X direction create an acceleration in the Y direction? Right? Is that possible or not? But
To me, it could be a tensor there. I don't understand why it could be a tensor.
Tell that again. Here.
You said the mass could be a tensor there?
I don't say could be, but to begin with, could it be a tensor? We know that it is mass is a scalar, right? As in Newton's law, mass is a scalar, but you could ask the question that can an acceleration in the X direction create a force in the Y direction? And that would make the mass a tensor quantity. And since this comes, since Newton's law we now know is not as precise as, at least in the gravitational context, it's not the way it should be, then maybe one can see what might be the case there. But in Newtonian physics, this mass is a scalar. But what I was trying to get to is, similarly, you're saying electric field in the X direction, can it create a polarization? This involves polarization, like D involves polarization. Can you polarize a material in the Y direction by creating an electric field in the X direction? And there are materials like that. In fact, that's what a birefringent material is. Like in optics, birefringent materials are exactly right, because this is a way of measuring in refractive index. Like we don't emphasize that very much in introductory level physics. This is the refractive index also. Just to get a picture of that, we'll see that this is not really real. This could be imaginary. This is in fact in the Fourier space, because this is our position, right? In fact, this equation itself is in the Fourier space. So that we usually don't write the R and T here, right? So one has to be careful, otherwise it's an integral equation. We'll see those things in a week or maybe 2 weeks or so. But what I was saying is that have this picture in mind, at least it helps to realize that this is square root of epsilon, very simplistically speaking. There's a lot of details that goes in there, where n is the refractive index. And refractive index, for example, if you take a crystal and you let light go through, sometimes if you change the orientation of the crystal, then light behaves differently. So that means to say that this material property is different. Again, we are jumping ahead. What I want to say is that there is a refractive index, and this could have different direction, or this could be a tensor, and that is the only point I want to make. And that is a very non-trivial feature the moment you. Here we have charge per unit volume creating an electric field. That means if you have a charge, that has to be a divergence of the quantity. In fact, if you don't have a charge sitting at a particular point, its divergence of the electric field is zero immediately. You don't have to do any calculation. There is no charge sitting there. It has to be zero. Divergence of the electric field has to be zero at that point. So in that sense, it is a slightly more information in there than the integral form of Gauss's law. Here we're telling details, microscopic details of a certain vector field. That suggests that there should be a similar thing about the divergence of the magnetic field. Might also have a source associated with it, but it turns out that this is zero. This is exactly zero. There are no source associated with the magnetic field at all. And that has to do with the fact that if, or let us say if this was not zero, maybe it is not zero and it's just that we have not measured it as of now. If that was the case, that would be called a magnetic monopole. Why is it called a monopole, single pole? It is to say, do with, we all know that a magnet consists of a north pole and a south pole. Right? That's how we visualize a magnet. Field comes from here. So this should be visualized as an electric field, also has a similar structure. If you have a dipole, then this is how the electric field looks like, right? That is E. And this is a magnetic field, right? This is symmetric, this keeps going. That seems to suggest that, oh, this is a dipole, electric dipole. So this is a magnetic dipole. So the question is, can you have a north pole on its own? Right? A good question, but as of now, we have never been able to isolate that. So since we have not been isolated, we have never isolated that, this is zero. But that's empirically true. A lot of theory, in theory, there is a lot of desire, you can say, that they really find a monopole, and there is a lot of nice, elegant conclusions you can come up with if that was not zero. Very non-trivial conclusions you can make if this was not zero. But for our course, this is always zero, until and unless sometimes we will say that's not zero and explore it.
Really quick question. You said,
yeah.
Maybe you were just relating it, but even if you were to just have a north, it wouldn't make sense to me that it would be a monopole because it's still made up of just charges. It would be made up of charges instead of like a magnetic source itself, like
the north pole is different from a positive charge. We are saying that north pole, suppose we say that such a pole exists. Now, currently, maybe what you're suggesting is that a north and a south pole, this is just a way of visualization. Actually, these are currents, right? That's one way of looking at it. Like these are currents, current I, a positive charge moving in circles, that behaves like a north and south pole, right? But that very quickly leads to philosophical argument as to what is the source of a magnetic field? Is it really a positive charge going in circles, or are there north and south poles existing that can do the same job? And usually that is not clearly, you cannot distinguish the two between the two situations. Does there really exist a north pole, which are always coming in combination of south pole, or actually these are just moving charges that create the magnetic field? It is not possible to distinguish them.
Okay.
Okay, so it's so the question here again, I think, is that moving charges, and that is how you will see that everywhere in our course, or even in the introductory level course, if you were to replace, so if you were to consider Q times V as your source, right? So Q times V is the same as IDL, right? So charge having a velocity V, if there is a flow especially, is the same as having a current times dl. So the source of magnetic field, is it this, or there is an actual dipole? So is it this, or is there an actual north pole, south pole? Is there a magnetic dipole? And this is a word given also. I'm not completely getting that word. I think it starts with M, where you say that this is actually a current, or there is an actual magnetic dipole in there. I forget the name of the person. So it's called a, this name is given to that proposition. So suppose there is a magnetic dipole, and let's say this is QM. This is not the actual charge, this is actually a magnetic charge, and still you can get all the physics out of it. And in fact, the question is, can you have such a thing? And we don't know that. Just looking at outside, whatever we are measuring, that's not sufficient to distinguish between the two. Maybe we will have some statements about that as we proceed. Usually in homework, you will see some examples where you will see if there was a magnetic monopole, what happens. Okay. Okay. So that's one thing. So Gauss's law for magnetic field in a local perspective is equal to 0. Divergence of the magnetic field is equal to 0. Otherwise, it will be the magnetic charge. So let me just, since this question came up, we can say this is rho m. That's what I was trying to. This is a magnetic charge, entirely new concept. It's not an electric charge that we are talking about. This is a magnetic charge. We are saying that that's 0. So it is like saying for every quantity that you see, or every matter that you see around yourself, we can associate a mass. We can associate an electric charge, which are completely independent of each other, completely new phenomena. And the question is there a third property, magnetic charge around, which is completely out of this system? If electric charge, moving electric charge can of course do the job, so that's a point. But is there any physics we are missing because we are not having this magnetic charge in there? And as of now, we have not seen anything. But if you were to introduce that, there are a lot of elegant propositions that, oh, you can explain this, you can explain that. One of the classic ones, again, yes, it's extra credit. These are the places where extra credit really helps. What I suggest is look up Dirac quantization. So extra credit. So look up Dirac quantization. What that means is that a very small gist, or the gist of it is that as of now, we do know that all the charges we see, so electron charge or protons charge or any charge that we see around us is in multiples of the electron charge, or there is a basic charge in terms of which there are integer multiples of that. And whenever we have such strong, clear patterns that one asks, is there a fundamental reason why that should be the case? Or is it just an accident? And usually when there is so many things there and there is a whole pattern, you say that's not an accident, there must be some other fundamental reason in there. And that quantization can be explained if you introduce the magnetic charge. If you say that there exists, or if you allow the magnetic charge to exist, or to exist in the Maxwell's equation, let's say, so then if E was the electric charge, the fundamental electric charge, and now there is a magnetic charge, let's call it G. Right? And it turns out that this will always be equal to some number times then H bar. I think there is an H bar there. And it will always come in this product. Right? But if there is no G, so then N is equal to 0, G is equal to 0, so that doesn't explain anything. But if G is there, then that gives you a very clear reasoning for that. And due to that reason, often there is a bias that, oh, this must be true. But as of now, we haven't seen. But then we are in a very small region of space, and we don't even know how to look for magnetic moment properly. Anyways, that's a diagressional level. For us, this is 0. That's the divergence of the field. This doesn't have a name for itself. We can call it the Gauss's law for the magnetic field. But usually there is no standard name for that as far as I know. Del crossed with electric field. So since I have defined it here like this, it's nice to write this as D. Right? And there is a pattern that comes out. This is D. So D is epsilon E and B is mu naught times H. I replace this D, and this is 0. And crossed with the electric field R, comma T, this is equal to minus the time derivative of the magnetic field comes up. In fact, it is nice to write this on the left-hand side sometimes. Right? This is plus, and we set that equal to 0. That's so better. Let me erase this and get this pattern better. So this is equal to 0. And D is equal to epsilon times E. And B is equal to mu times H. This is for a general material, but if there is no material, this is called the epsilon naught. So in general, it is just epsilon. In vacuum, this is epsilon naught.
Otherwise, E is the ER, whatever the material is, times epsilon naught. Is that what it is?
Otherwise, it is just epsilon. So epsilon is the dielectric constant, no, dielectric permittivity, let's say, electric permittivity. Right? Not that dielectric is a ratio. Electric permittivity of the material. And mu will be the magnetic, then you don't need the word electric, so permeability of the material. Vacuum also is treated as a material, and in the special case, that becomes epsilon naught and mu naught. Is that clear? Okay. And the ratio epsilon over epsilon naught is considered the dielectric constant, but we'll come to that like as we reach. This is I'm just summarizing the whole thing. Del cross H plus or minus. So let's change the sign. Minus E by dt is equal to J. Where J is the current density. That's current per unit area is J.
Shouldn't it be mu naught J?
No, because okay, what you are having in mind is
Oh yeah, you have a
H. Notice
Okay. Okay. Yeah.
I changed it to H. So that's an advantage of writing it this way, and all that doesn't show up, right? It's all hidden. Like this has a so what Jordan is saying is that this should, if you write this as D, and this should be D. Maybe that's what you're looking for. This should be D. So I made a mistake. This should be D, epsilon. Right. So if you write this last equation in terms of B, H is B over mu naught, then this will become a mu naught times epsilon naught, and then this is dE by dt is equal to mu naught times J. And remember, mu naught times epsilon naught is equal to?
So 1 over c squared?
Yes, good. Very good. So it's 1 over c squared. Right. So this will have a 1 over c squared. If you want. Yeah. Keep it as it is. Okay. But we will stick to this. Now, these are all Maxwell's equation in SI units. And we will stick to SI units all through. But it turns out that it couldn't get any worse than this, right? Already, when you're doing introductory level physics, you see a lot of issues with units. Everyone likes to use their own units, and in principle, everyone should use their own units. Perfectly fine, as far as they're good at conversion. What one should teach is not to use a single unit. In fact, to make sure that you don't make errors in conversions. But errors are there. So if you're not sure that you won't make mistakes, then it's better to have a universal unit. So it's not that universal is good by any way. It's usually not good, because then you're using only one thing and you're not exploring other things at all, even though there's not much in here. But it is good if you can avoid making errors. But it is hard to make, hard to not make errors. That's the point. Now here this gets worse, right? There it is just numbers that change. You never say that F is equal to MA is written in a certain units. Whether you write this in MKS units or in CGS units or any units, F is equal to MA is F equal to MA. That equation doesn't change. But in E&M, the equation changes. It's not just the numbers that change. The equations look different. So what do I mean by that? So for example, the first equation that we wrote down, so let's write that down again. So in SI units, right, the first equation is del dotted with E, right, in vacuum. This is equal to rho over epsilon naught. Right. That's your Gauss's law. Or maybe I should have given names there, right, before I go there. This is called Faraday's law. And this is called Ampere's law. Probably. And Ampere's law, one should know that Ampere's law involves only del cross H is equal to J. And this was introduced by Maxwell. Are you familiar with what I mean there? What's the contribution of Maxwell in the fourth equation? Anyone?
Changing electric field causes a magnetic field.
Yeah, that's correct. How did he find that out?
How did he find it out?
Yeah, he did not do an experiment, by the way. So that's a good extra credit problem. Yeah, extra credit problem. Describe, I don't mind if it is in detail. I would say spend time on it. That's a very good point to realize. Describe how Maxwell found out. He gave an argument, like it was a pretty much a logical argument. He said that there has to be this term just by a thought experiment, logic basically. Describe how Maxwell found out that dE by dt should contribute. It's a very beautiful argument, so it is described everywhere. How about this? I expected somewhere in the exam also, so that you really figure this out on your own, right? It's a good argument, but extra credit problem also. Okay, so what I was doing is change of units. So, has to leave. Okay. So, in SI units, Gauss's law looks like this. In Gaussian units, called Gaussian units, the same equation looks like this. 4 pi rho. And this is a disaster in the sense, if you're not familiar with all these units, you come, let us say you're in 10th grade and you've never seen Maxwell's equation in detail, and you suddenly have a brilliant idea. You say that, oh, if I do this, I can generate this, and you would like to check. So you would like to put in some numbers. And if you try to ask, okay, what is the electric field that something will generate? Which equation do I use? If I use this equation, I'll get some other numbers. If I use this equation, I'll get some other numbers. If I don't do it carefully, and I use the correct dimensions for the quantities that are involved. So that's the challenge. For example, there is this quantity called fine structure constant. This shows up in your homework also, fine structure constant. We won't get to talk about it too much in the course because it's an advanced topic, but a nice way to look at it is that there is one parameter that describes the whole of electrodynamics, and that's this fine structure constant.
Is that an alpha?
Yes, that's an alpha. Let me make it a little bigger. Alpha, that's equal to, now sometimes you will see this is this. Right? And in some other books, you will see this is E squared over 4 pi epsilon naught h bar c. Okay. And now you scratch your head and say, how is it possible? Right? How can two things be the same? Like, that's impossible to have that. And that's because this is written in 2 different units, right? One has to realize that this is in Gaussian units. So your electric charge, such a fundamental thing that we say is in SI units is 1.9 into 10 raised to minus 19 coulomb. That's an SI unit quantity. It is different in Gaussian units. It's it's called stacked coulomb there.
So that's
this is
basically
SI.
where all the 4 pi's come from?
Yes, that's correct. That's exactly correct. So that's called rationalization in units. And if you read up about all this, it's very interesting how these things go by. I mean, how you set your units and all that. Remember that recently, 2005, I think, we changed all our units. All our standard units have changed. Now it is all with respect to constants. For example, speed of light is a number now. It's an integer. It is no more a measured quantity. C is said to be an integer, and then everything else gets derived out of that. So it's kind of nice story if you read up about it, how people went by fixing the units. Actually, recently someone told me in US there is this 2 feet, right? One is a US feet and there's an international feet. So those are slightly off. And apparently they are retiring one of the units, so or one of the units. So that's what someone told me. And it's good to see what goes behind all these things. There's usually a committee sitting and talking to each other and saying, "Oh, this is better than the other." But in principle, you can use anything as far as you know how to convert, and conversions are not easy, as you will see in here. So so what I say is that the same equations, all these equations can be rewritten in Gaussian units. So the most popular units are SI units. Actually, that's also a good point to say that half of physics textbooks are pretty much half, exactly half, are written in SI units, and the other half are written in Gaussian units. And few are written in Heaviside, Lorentz Heaviside units. So let's say Heaviside Lorentz. Now, I use SI units in this whole course, and the next favorite of mine is Heaviside Lorentz units, and Gaussian is the third. But I should say, why is this so popular? All application-oriented books, basically engineering books, really that deals with experiments, typically deals with SI units. And that's mostly because electrostatics and magnetostatics work out very well in SI units. There's not much clutter there. But if you were to do radiation in SI units, you will see that there is this epsilon and mu naught showing up everywhere, especially in material physics. It is not convenient. So often, to avoid clutter, you like the idea of Gaussian units. So all the theoreticians, especially, like Gaussian units. And in fact, some of the books change units right halfway. Right? You will see half of the book is done in SI units, and then you will change, oh, now I'm going to use the moment relativity comes in. That's when all this happens. The moment you want to introduce relativity, that's basically radiation if you want. That's second semester of our course. And you'll switch over and say that I want to use Gaussian. And the most popular book, which is an extremely nice book, Jackson does that. Like halfway, after 7th chapter or so, they will say that, okay, now SI units is no more, it's too much of a burden to carry on with SI units, so let's switch over to Gaussian units. So you have to be very careful when you're looking up your equations in a textbook or on the internet, And you should be able to convert this. No one will write this G subscript for you. It will be very convenient if everyone always wrote, oh, I'm using G subscript and doing that. But that's not done. Textbook in the beginning will say that this is the units I'm going to use. That means that E is in Gaussian units. And then you have to switch over between the two. And your homework problems deals with this. I give you an equation for you, and then you have to work out how will it look like in another set of equation. And the conversions itself are reasonably self-explanatory. So first problem deals with that. So with that, let me proceed and go to what we can learn from Maxwell's equation. Right, so that's all about units. I'll leave that to you and the homework to convert between the two. You'll get a feel for conversions in that. Okay. So let's do something what you can do with the Maxwell's equation, and let's start with the first Maxwell's equation, which is epsilon naught E, and we are in vacuum. Whenever I write epsilon naught, that means I'm in vacuum. There is no material involved. That's your rho, right? That's the first equation. And all this RT dependence is implicit in this. Let me take a time derivative of this. This is valid at each position and time. So let me take a time derivative of this. Started it. Let me write the epsilon naught. I think it is. No, let's just stay there. Probably let's stay. That's equal to d rho over dt. So notice what I'm doing. Maxwell's equations will be considered fundamental, and we will try to derive everything out of that. And any mathematical operation you do on an equation, that's, if it is valid, that's a new thing, also has an interpretation, right? So this is a true statement if Maxwell's first equation is correct. Let's start with another equation of Maxwell, and that is that del crossed with H is equal to d by dt of epsilon naught E plus J. I wrote this up to the right hand side, doesn't matter. So that was the first equation, and this was the fourth equation, the way I wrote it down there. And in here, let me take the divergence of this. Divergence of this fourth equation. Equal to divergence of d by dt plus okay. What is the divergence of a curve?
Zero.
Zero. Very good, right? It is always zero because of the symmetry properties, right? We can use, say, Levi-Civita symbol and so on to show that that's equal to zero. So this implies this, and this implies this. Now I'm going to combine the derived equation. So this is zero is equal to. Now notice a spatial derivative and a time derivative can be interchanged. All through we are dealing with functions where this property can go through. They are very broadly called in a sloppy manner well-behaved functions. Right? But we there was an extra credit problem on that, and some of you guys really tried to get that. An example of a function which actually does not satisfy that, and I also gave links to where you can find out, and we will actually do that in complex analysis in in our math methods course, we will do examples where we will see this. So, but we are dealing with cases, or at least most of the time in regions where that is perfectly valid. And if that is the case, this can be replaced with this. If I can swap this partial derivative with position and time, then I get you this, and this is d rho over dt plus del dotted with j. And that we say will be an important statement. So this is, I'll write the 0 on the right hand side. So, and we would like to have an interpretation of this. This is a derived equation. So this is called a continuity equation for charge. Let's say for charge density. This has nothing to do with electric charge or anything.
So I have a question here because
Yes.
isn't that supposed to be negative then?
Why is it negative? Is it negative? No.
Isn't the continuity equation d rho dt minus
No.
del dot j?
No. Any continuity equation will always be this form. In fact, this is much more like it's a fluid dynamics thing. It will always be positive. At least the way typically it is written. If you define it in certain other form, maybe it's possible to do it. But
if you started with the integral equations, then you would get negative because you'd change your surface integral to volumetric
No.
No?
you shouldn't. You shouldn't. No.
Okay.
Pretty standard, I think. Again, it's a matter of definition somewhere, but it's pretty standard that it is positive. Let me know if you see places where it is negative. How about that?
Okay.
So, yeah, I think it is pretty standard in fluid dynamics. So, fluid dynamics is where this shows up. And it can be with mass, water, velocity. You can do continuity equation for various things. So, let me quickly make 2-minute conclusion. I'll go very fast. If I do an integral of this per unit over volume, so this becomes an integral of charge density, that becomes charge, and this becomes integral of the divergence, that becomes a surface integral of the A dotted with J. That's equal to, now this is 0, that's important, so this is 0. Let's say that, what if this was not equal to 0? Let's say this was some source S. Right? This is actually 0. But I can think of this as some source S. This is 0. Okay? You write that as 0 is equal to S. That's just to give you an interpretation in there. And that has a meaning now. So think of it as any volume that is charge Q. What this is saying is that, and I like to compare this with a population, this has to do with how many people are born or die inside a population, or how many charges are created or destroyed inside of this volume. This has to do with how many charges cross the boundary, flux. This is flux, how many cross or come in, either way. Right? That's okay. And this is the source. Did I say that correct? No. Earlier what I said, how many charges are created or destroyed is this. This is source or sink. Right? This is flux. If you think of a country, how many people are coming in or going out, this is how many people are born or dying. Right? And this gives you the population. The rate of change of population of any quantity is equal to the source or sink, how many people die or are born, plus how many people are coming in or going out. That's a simple statement. That's a continuity equation. And this can be for any property. We will deal with charge. We will talk about what are the sources of charge. So what this statement is saying, a very strong statement, is that there is absolutely no source for a charge. There's absolutely no source for a charge. Right? Charge cannot be created or destroyed. Right? Whatever you have, that's all you have. In Maxwell's equation law. Later we'll talk about virtual particles that you can create and destroy. But then total charge is never created. You will always create plus and minus. So in that sense, charge is locally conserved. So this is called the conservation of charge. If you have 10, when the universe was born, if you had 15 charges to 15 coulombs of charge, that's it. You have no way of creating it. It is 0. So that 0 is very significant. And it's not an accident. Maxwell's equation implies that this was not a statement we cooked up. This is an implication, that's a derivation of. Let me stop here and I'll talk about it more.
Excuse me.
Yes, please.
I have a question, please.
Yes.
You said that the charge cannot be created or destroyed?
Yes, it cannot be created or destroyed.
Wow. I mean, if we have, like, as you said, 15 columns.
Oh, maybe I should say that, maybe let me refine the statement. I can create a positive and a negative charge. I can create +3 and -3, but I cannot create +3 charge. If the total charge of the universe is conserved.
Ah, I see.
Right? If it was +13 to begin with, it is +13 forever. I can say there are +15 and then -11 kind of, right? Or how do you say it? -2. +15 and -2 will again give you +13. That's okay. That's the state. Okay?
Well, I have a question, but I cannot crystallize it. So, sorry. Let me think about it again.
Sure.
Uh-huh.
Yeah,
I was thinking about the idea of creating a current or charge or putting them into work, like, and the only thing we can do that transferring charge from one side to another, is that the idea? We cannot destroy them.
We cannot destroy. I mean, we can, okay, maybe I'm giving a wrong impression. If you have energy, you can create a matter and antimatter. That's possible. But matter and antimatter have positive and negative charge. So total charge you created is 0. So you cannot change the total charge of the universe. I think that's what I'm saying.
Yeah.
That's my point.
Yeah. Also, my question is not that clear. I'm sorry. So it's not kind of clear idea in my head, but it kind of sparked something in my head that you said that. It's I mean, very surprising to know that.
Yeah. Any conservation theorem is beautiful, and we will see that there is a bunch of conservation theorems in this. Only thing that will be S won't be always 0. S being 0 is remarkable. That's the implication. We will talk about electric field, energy of the electromagnetic field, momentum of the electromagnetic field. Each has a continuity equation, and that will be the spirit in which I would like to take this course. That we talk in terms of electromagnetic energy, electromagnetic momentum, electromagnetic angular momentum. That's what we would like to talk about, but you cannot go too far with that. A lot of baggage you have to carry. So at least the beginning I'll try to.
All right. Thank you very much.
Yeah. Thank you.
Thank you.
Okay, bye-bye.
Bye-bye.
Right. I have a question for you.
Yeah.
Can you see this
Go ahead.
board?
Come again?
Can you see this board?
Oh, yes. Yes. I think I can pin it down so that others can see, I suppose. So, yeah, now, as far as they're allowed, you guys can leave if you want, so you guys can be nice to Jordan and listen.
hold on. I wanted to ask you because
Uh-huh.
so
Please.
if you said, you know, I'm gonna draw this big. Can you even see that?
Yes, yes, very clear.
Okay. So Q is equal to this, right? The volumetric integral of this guy,
Mm-hmm, mm-hmm.
right?
That's correct.
That's the change in the electric charge during some interval. So, or this is. So if I write delta Q is equal to change in time, partial by partial t, the volumetric integral of rho dV like this. So that would be the total amount of electric charge that's passing through the surface during that time interval. Okay, and then if you wanted to do the other part, so the part that's just through the surface, then you have another delta Q, but it's like, you know, some other Q is equal to delta T times the surface integral of this.
Yeah.
Conservation of charge, you set them equal to each other, right?
Mm-hmm, mm-hmm. Yeah.
And then you get, you know, if you say delta Q is equal to delta Q because of the conservation of charge, when you put them together and solve, you get d by dt of what we just did, rho of the volumetric integral is equal to the surface integral.
No, what you would say is plus, right? Not equal. It will actually be plus that equal to delta Q, right?
I set the Q's equal to each other. I set this equal to this.
Why?
I canceled the delta T's. Because
no, the way you should say it, I think, is delta Q is the charge,
you're
change
saying
in charge.
delta Q plus delta Q.
Tilde, it should be equal to the delta. No, it is 0, yes, but it should be the change in delta Q, which we say is 0 because it's an implication from the Maxwell's equation, yes.
So you're saying, well, I'm saying that if the amount of charge contained in is exactly equal to the amount of charge that's passing through the surface, then why couldn't you make this statement?
Because that depends on your surface integral. Is it leaving positive or is it coming inside is positive? When you make a surface integral, usually you say things that are going out are positive.
Right. So all the charge contained inside of whatever surface has to be equal to all of the charge on the surface as it leaves, right?
Maybe that's where the point is. When you think of a surface integral, I think what you're saying is the opposite of the usual surface integral. You want to be inside the volume, but then you're using the notation of going outside the volume. Check that out. I think that's where the confusion is. I think. Okay.
Okay. Because then, you know,
I see your point. Yeah.
Yeah. And then you had, you know, del dot J.
Yeah.
This is just from the Gauss's theorem or whatever. And then.
Yeah, I got it. So when you say delta Q is equal to get delta Q tilde, I think that's the point. What do you mean by delta Q tilde? I think you want to question that, or just the sign of that. Is that the charge that is entering the system, or is that the charge that is leaving?
Negative?
It is a matter of definition. What do you mean by that? Okay, so let me write that down again here. So for example, if I have to switch right now. So when you say this quantity here, dA dotted with J, right? Right. What does this mean? Right, that's what we're asking. Right, this is a closed integral. Is this meaning the charge that is leaving the system, or is this meaning the charge that is coming into the system? Right. This is called the flux of the current that is going out. So usually there is a notation that this is the normal vector, right? That's your right. So with respect to that, I would say that this is going out. So how many are going out? Right? And probably what you are saying is how many are coming in. You see what I'm saying? That will change the sign immediately.
Yeah, I see what you're saying, but
So I'm not trying to say that what you're doing is wrong. No, I'm not saying that. I'm just saying that might be the source of the sign change that you're talking about. You see what I'm saying?
yeah, no, I get that, but I guess
And now that you say it, maybe there are books who really like to say this as this is the negative of that, and you would put that as a negative sign and put it on the opposite side, which is okay, I think, as far as, yeah, that's okay, I mean, in principle, yeah. With that definition there, I think that's okay. If that helps. Right?
I just wanted to make sure I wasn't thinking like I was missing something.
I would say think of the zero also. I mean, I'm not sure whether you're missing that or not. Try to interpret that zero also there. Like put in an S there and what does it mean? Charge conservation is...
To me, if it's plus or minus, it means the same thing though. That zero represents...
No, what I'm saying is what if this was not really zero? There are situations when S is not zero, not the charge, something else. We will talk about electromagnetic energy. Maybe I should give you a hint of what we're talking about here. I would like to very quickly talk about d by dt of energy, right? Same equation notice, plus divergence of something else. This would be called a Poynting vector, like the flux of energy. And this time, this won't be zero. Right? This will be, in fact, it will be, this usually, I like to write it on this side. This will be J dotted with E. That's equal to zero. And the same interpretation goes in here. This is a change in energy. This is the flux of energy, whatever you're saying, at the boundary, whatever happens. And this is the source of energy. Like where
now you have a source.
Now you have a source. That's what I'm trying to say here, that this is a simpler form. Whatever you said is perfectly correct. And it works very well in this case. But
as long as you don't have an external source of energy.
Exactly. That's my point. Okay? So it's okay. I'm saying, as far as I see, you're not missing anything in the context of charge.
Okay.
Does that help?
Yeah, that helped.
Yeah.
Whenever I saw the plus, I didn't understand. I'm just from maybe my undergrad or something. I just remember it being negative, and
maybe I went too strong saying that was positive. I think it is positive in all the books that I have seen, but maybe it's all graduate level book. Maybe.
Okay.
I don't know. I don't want to. Now that you pointed out in this way, I said that okay, maybe there is a notation change that you can change, but it's okay. I'm saying as far as you know the definition, it's okay. It's like the work done, right? Often in work done, you always say work done by the force is positive, work done on the system is negative. So it's a matter of what the definition is.
All right. Thank you. That's helpful.
Yeah, we'll come back to this. We'll use this in the next 2 weeks a lot. So you will get an opportunity to.
All righty.
Okay.
Bye, people.
Yeah.
Thank you.
Thanks.
And
bye.
whenever these discussions extend, you're all free to go. But of course, you're allowed to be there. But don't feel compelled because I'm there. Okay.
No, it was helpful anyway. Thank you.
Good. Okay. Okay.
Thanks.
The bootstrap for Jordan. Jordan speaks and no one listens. That's not fair, right? So that's also good. But that's as a friendly thing. It's not a requirement for the course.
Nice.
Okay. Good, guys. Yeah. Good discussion. Thank you.
Bye.
Yeah.